Here's a slight extension of the result we just talked about. So suppose f is a family of holomorphic functions and they're equibounded then I claim that the set, let's call it f tilde of f prime, so f belongs to f, is also normal. So previously we showed this family is normal. Now I claim the family of functions we get from taking the derivative of this family is also normal. Tell me why that should be true, given what we proved last time. So how did we prove the result last time? We took a compact subset, Kp, right? Like this. And we knew it had a certain distance away from the boundary, 2 to the minus p. Yeah. So then we took this epsilon neighborhood of the set like this, or this, not epsilon, but this 2 to the minus p minus 1 neighborhood of this set, like this, yeah? And then we showed that on this, the set of derivatives are uniformly bounded. So f prime, let's write it like this, s prime L infinity, since it's smooth, let's just write C0 on n 2 to the minus p minus 1 of Kp was less than this constant m from the bound on this entire family, and then 2 to the p plus 1, right? That's how we proved things last time, yeah? Which meant inside this set, this family of functions were Lipschitz, uniformly Lipschitz with uniformly Lipschitz constant, and therefore equicontinuous, and therefore we could use Escolio-Zähler and find a convergent subsequence on that set, and then the diagonal argument. Okay, so now I'm claiming this also holds when we consider the set of derivatives. How does it hold? And what was the key? How could we prove this? What was the thing that made this work? Yes, so tell me how. So let's do what you say. So take Z1 and Z2 belonging to our set Kp, yeah, with mod Z1 minus Z2 less than 2 to the minus p minus 1. So in particular, Z1, that's what I like, Z2 belongs to the neighborhood of 2 to the minus p minus 1 of the set Kp, because Z1's in this, yeah? And in particular, we have that the interval, the line segment, oops, Z1, Z2 is contained within this set. Right, that's exactly what we did last time. And previously we used the fact that on this set we have this bound on the first derivative, yeah? But since we're trying to show that this family is equibounded, is equicontinuous, we don't need this bound, we need a different bound. What bound do we need? There we go. So this is by Cauchy integral formula. But by Cauchy integral formula for the second derivative, or any, we have this for any order of derivatives, of course, we have, well, let's just write down Cauchy integral formula for the second derivative. Yeah. We also have that the second derivative at z is we have 2 over 2 pi I, the integral of f of zeta zeta minus z to the power 3 dz over the boundary of a ball of whatever radius we want. So, but we're going to 2 to the minus p minus 1, like this, you know, centered around z. So I can't fit that in. Okay, let me write that better. 2 to the minus p minus 1 around z, like this, yeah? And then the same thing holds, right? So this thing is uniformly bounded above. This thing on the bottom, it's never getting smaller than 2 to the minus p minus 1 to the power 3. So we just do the same estimates, and all that happens is that this thing gets a bit worse. This thing becomes this thing squared, yeah, when we have another derivative here. Yeah? You guys all see that? Give me a thumbs up if that makes sense to you. Okay, perfect. Good. So then the argument's exactly the same, right? So we have a line segment contained within this thing, and on this set we have that the second derivative is actually uniformly bounded, so therefore the first derivative is Lipschitz, f prime over z1, f prime over z2 is less than this universal constant from the soup of all these functions in the family f, and then times this 2 to the p plus 1 squared. So, but it's like 2p plus 2, like this. Yeah? For any z1 and z2, such that this is less than this. Yeah? So f prime is equicontinuous on Cp, and then the thing just follows as before. Cool. All right, so we have something even a little bit stronger for normal families, for families to which the function is equibounded and are holomorphic. Now, the next result is the one I mentioned before, that if we have a sequence of functions of omega, let's start to C, such that Fn tends to F uniformly on compact sets, and obviously Fn are holomorphic, then either holomorphic and injective then either F is constant or injective as well. And I asked you to think about this. Okay, suggestions for how we might approach this. How could we approach this? So I asked you to think about how do functions in complex analysis fail to be injective? What are examples of functions that fail to be injective? What are simple examples? Say that again. Did you say z to the n? Yeah. So examples of non-injective z to the p for any p bigger than or equal to 2. Yeah? So if we had a function f that was just this thing, so if f of z was z squared, why is it the case we don't believe that there is a sequence of functions fn that are injective that uniformly converge to this on compact sets? Why would that seem not possible? I'm going to raise the board. You guys think about that and try and tell me why you don't believe that can be the case. Yeah, so the image of a circle going around the origin, so let's assume omega contains the origin, the image of a circle winds around twice, yeah? So why is that a problem for us? Why does that mean we can't have a sequence of injective functions converging to z squared? Okay, so maybe you're heading in the right direction, but what I wanted you to say is that if we have z squared, what does it do? It takes the complex plane and it does this thing, wraps it around itself one time like this, yeah? And if we have a sequence of functions that is uniformly converging to a function that does this, then it's also going to have to do the same thing, right? If a function is very, very close to behaving like the limit function, and the limit function takes the entire complex plane and wraps it around, then if you take the image of a circle going around the origin, then for large enough n, that thing is going to be forced to wrap around twice as well. Yeah? Just because it's close in L infinity norm, right? So, if omega was just the ball of radius 1, f of z was z squared, then let's take for any r between 0 and 1, f of the boundary of the ball of radius r of 0 wraps around twice, right? Twice around. Yep. So if this is our domain, then the image looks the same, but we're going around 2 times. Huh? So I'm overlaying it to make it look like it's 2 times, right? So if we have a function that is doing this, and then fn is uniformly close, that means fn around the boundary of this ball has to be doing something very, very similar, right? It has to be within some epsilon of doing the same thing, yeah? And if it's within some epsilon of doing the same thing, then it's forced to wrap around twice. But if it's wrapping around twice, then that means it's actually not injective, right? Yeah? Okay, cool. So, this special case gives us a hint of what we should use. Huh? We should use the fact that if things fail to be injective, it's because they are wrapping around each other. This is one of the very special things about complex analysis, that we can understand various phenomena like zeros and singularities extremely well. So we're going to try and use this example to provide the proof. So what's the natural tool to look at? What's the natural tool? What's the natural tool to apply, given this example? The argument principle. The argument principle. Okay, cool. Let's try and build the proof. So, proof. We have Fn tends to F uniformly on compact sets. And suppose F is non-injective. Suppose that F is not injective. All right, so there exists Z1 and Z2 belong to omega such that f of Z1 equals f of Z2. Okay? F, by easy things, is itself a holomorphic function. This is a question you sometimes see in prelims. Can anybody quickly tell me why we know that? Morera's theorem, yeah, that. Morera's theorem says that if we integrate around every single closed loop and it's equal to 0, then it's a holomorphic function. So if f is the uniform limit of functions that satisfy this, then we can pass the integral through, pass the limit through the integral sign because we have uniform convergence. So it's also true for f, and therefore f is holomorphic. Or we could just prove that f satisfies Cauchy integral formula. Same argument. If we satisfy Cauchy integral formula, then we can differentiate, and therefore it's holomorphic. Yeah? Cool. So f is holomorphic. We know that for sure. So we have z1, z2, so that this is true. And we're going to define g of z to be equal to f of z minus f1, like this. This is also a holomorphic function, and so is this thing, gn of z, which we define to be fn of z minus f of z1, like this. So gn tends to g. So I'm going to try and abbreviate this uni on CC, uniformly on compact subsets. Compact, that should be UCS then, subsets. Yeah. Just as before. And notice that g of z1 is equal to 0, but also g of z2 is equal to 0, because f of z2 is equal to f of z1. So we have that z1 and z2 are both zeros. And g is holomorphic, so the zero which is at the zero that is at z1, I mean, both of them are isolated. They are both isolated zeros. Yeah? They are both isolated zeros. But we don't have that they're both zeros of gn. So we do have that z1 is a zero of gn. No, we don't have that either. Did I do this definition wrong? I think I did. I think it should be like this. Yep, that looks better. Yep, that's it. So gn of z1 is indeed equal to 0, but fn are all injective functions. So gn of z2 is not a 0, right? Gn of z2 is definitely not a 0. Yeah? Cool. Now, there exists some potentially quite small such that g of z is not equal to 0 on the z, on the boundary the ball of radius r around z2. So z2 is an isolated 0. Yeah, so there might be some other zeros getting somewhat close to this, but we don't have a cluster point of zeros, obviously. So there is some radius where there's no zeros around the radius. Yeah? Because it's an isolated 0. Yeah? And that's all that we are claiming here with R1. Yeah? Cool. So articulate means that this thing is bigger than 0, bigger than some particular constant just by continuity. I.e. the infimum on the boundary of the ball of radius r around z2, g is bigger than, let's call it some constant c, which is bigger than 0. Yeah. Because if that wasn't true by continuity, it would be a 0. Yeah? Cool. All right. So what are we going to try and do? We're going to try and mimic this special case. And since G has a 0 at Z2, yeah, then it should be doing some kind of wrapping around. Right? So by the argument principle, we have that the integral of 1 over 2 pi I of the boundary the ball of radius r of Z2 of G prime over G dz is the number of zeros, counting multiplicity, minus the number of poles. Yeah? But there are no poles, so it's just zeros. So it's the number of zeros of G in this ball, the R of Z2, like this, which is at least 1, right? So this is bigger than or equal to 1, because we have a 0 there. Yeah? Cool. But if we consider this expression, what is this? What is this? Why? Just Gn is injective. Yeah. So there's no other point. Yeah. Fn is injective, and therefore Gn has no zeros at Z2 by the way we've constructed it. Yeah. The only thing that's a 0. Go ahead. So we have to choose little r such that this thing is non-zero on the boundary for, sorry, G is non-zero on the boundary for a reason I'm about to give. What is C1? Do you say Z1? Yeah, we need Z1 not to be inside this small ball. Yeah. So, but that's also by definition, because I said that it's the only 0 inside the ball, and Z1 is also a 0 of G. Yeah. But yeah, you're right. Cool. So we know that this thing is 0 because Fn is injective, and the only thing that is a 0 for Gn is when we stick in Z1 like this. Yeah? So Z1 is the only 0 for this guy. Yeah? And Z1 is not inside the ball, as Sanaska just pointed out. Yeah? Cool, so this thing is 0. All right, how can we go further then? How can we use these things to get a contradiction? The uniform convergence of Gn on compact sets. Okay, so let's look at this expression here. Let's look at this expression. How are we going to manage that? So the point is that since we have that Gn is converging uniformly to G, and we have that Gn prime is converging uniformly to G prime, this is the slight extension of the previous theorem we just talked about, yeah? Then this quantity we can control uniformly. So note that G prime over G minus Gn prime over Gn, this thing can be made uniformly small, right? controlled in terms of how close G is close to Gn and G prime is close to Gn prime. Because, as pointed out, G is not equal to 0 on the boundary. If G was equal to 0 on the boundary somewhere, we'd have a problem. So we'll use the standard triangle inequality and break this up into two pieces that we can understand, right? So this is less than or equal to Gn over G, and let's maybe do Gn prime over G like this, and then do Gn prime over G minus Gn prime over Gn like this. Yeah? And then we could control these guys. So this is less than Gn prime minus Gn prime over the infimum of G on the boundary. So running out of space, I'm just going to write like this. And what about this thing? This thing, we can just pull out this Gn prime, let's take the supremum of it. Again, it's bounded by the same kind of arguments that we've had before, because on a compact subset, this derivative is bounded. And we have that this is 1 over G minus 1 over Gn. Like this, and we can make a common denominator. And since G and Gn will be uniformly bounded below, so long as n is sufficiently large by convergence to compact subsets, then this thing will also go down to 0. Yeah? Are you happy with that, or shall I put more details into this? Give me a thumbs up if you're happy. Okay, looks like everybody's good. All right, so that's it. We can show that on compact subsets, this expression tends to this expression uniformly. Yeah? Uniformly. So in particular, on the boundary of the ball, it's true, yeah? Which means we can pass the limit through the integral sign. We can take the limit of this thing and pass it through the integral sign and have that this is this thing, but that's a contradiction because this thing should be bigger than 1, but this thing is actually equal to 0. Yeah? Cool. So what we used was an argument that follows this structure of this special case very closely, right? Because in this special case, we thought, okay, this seems really unlikely because if we have the limiting function as Zn, then the image of a circle gets wrapped around twice. And if we have uniform convergence, it's forcing the image of a circle for one of these sequence elements which are close enough to wrap around twice. Yeah? Yeah? Cool. All right. Okay, a bit more background we need for the statement of Riemann mapping theorem. Firstly, let's recall what simply connected means. So we say gamma 1 and gamma 2 are homotopic if and only if they're curves with the same start and end point. So this thing was this thing, and okay, and there exists a family gamma of S from A to B, where gamma S of A is the same as these endpoints, and gamma S of B, of course, is the same. Damn it. Okay, and as a function from, say, t to s, going to gamma s of t is jointly continuous. Okay, so the picture, of course, is more clarifying. So if this is the first path, gamma 1, and this is the second path, gamma 2, then we can find a whole family that smoothly go from being like gamma 1 all the way to being like gamma 2. Yeah? That's what a homotopic, that's what two curves being homotopic means. And we say something is simply connected, so omega is simply connected, if and only if every simple closed curve, yep. No, it's definitely not unique. No, there's plenty of them, yeah. If and only if every simple closed curve is homotopic to just a single point, to a curve that is just the identity curve of just being constant at a point. A point. Which means that if we have our region, every simple closed curve, we can smoothly deform it while we're staying inside the region down to a single point, yeah? Which is a way to say that we have no holes inside our region. So if this is our region and this is a hole, then, for example, there's no way to smoothly deform this simple closed curve down to a single point while remaining inside the region. Yeah? So this is the beginning of algebraic topology. This is the fundamental group. This is where these notions start to come out, and it's a crucial notion for us in complex analysis. All right, cool. So that's what a simply connected set is. Yeah? Okay, a bit more background. So we're going to follow Stein's definition of conformal mapping. So in Stein, that means we have a biholomorphic mapping, a bijection between omega and its image, where it's holomorphic and its inverse is holomorphic. So is conformal. If and only if it's a biholomorphic mapping. From omega to its image. Okay. Like this. And we need a bit of background on Schwartz's lemma. So I don't know how to spell this, something like this or the reverse. Maybe it's TZ, maybe it's just Z, whatever. Schwartz's lemma. So what does this say? It says that if f from the unit disk into the unit disk where holomorphic and f of 0 equals 0, then we have that f of z is less than or equal to mod z, and if we have that for some say z tilde belonging to D, which you have an equality, f of z tilde is equal to this, or if we have that f prime of 0 is equal to 1, then f is affine, so it's just a rotation, i.e. rotation. Okay, so why is that the case? Just by looking at the following thing, so just briefly, just consider the function g of z equals f of z over z. Yeah. So this thing for sure is perfectly nice and holomorphic, except potentially at 0. Yeah, except potentially at 0. But since we have f of 0 equals 0, this is the same as f of z minus f of 0 over z. Yeah? Yeah. And we know that f is holomorphic. Yeah? So limit as z goes to 0 of g of z is nothing other than f prime of z. Yeah? Like this. Yeah? So that means that this function g actually has a removable singularity, and we can remove it by just sticking in the value f prime. Yeah? So that means g is actually holomorphic on the entire disk. And then what? Well, then by the maximum principle, it should have the case that the absolute value of g takes its maximum on the boundary. So g of z is less than equal to the supremum on the boundary of the disk. So I haven't said it, but the disk is just the ball of radius 1 at 0. Okay, so it's less than this thing, absolute value of g, like this. But that's the same as, we put the absolute value of this thing, that's the same as the sup of, on the boundary of this thing, of this guy, but we're mapping into the disk, so then this thing is less than equal to 1, and therefore just putting the z on the other side gives us this inequality, right? So Schwartz is fairly straightforward if you just write g of this form, and the other parts of it follow because, again, the maximum principle. If we had a z tilde for which this thing was an equality, so where did I write it? If we had this thing, that would be the same as g of z tilde having absolute value 1, yeah? Somewhere inside the disk, which is only possible if it's constant, again, by the maximum principle. Yeah? Yeah? And the final part follows as well, that if this thing is equal to 1, then the limit, well, then g of 0, which is equal to this thing, is equal to 1, and then, again, we get a contradiction, yeah? By the maximum principle, unless the thing is affine, just a rotation. So that is Schwartz's lemma. Oh, final thing, let's squeeze it in. Okay, let's erase the board, and for the final thing, and then let's try and state Riemann mapping theorem and start the first part of it. Characterization of all the diffeomorphisms, holomorphic diffeomorphisms from the disk, and they're given by this. I think it's given by this. Is that correct? Yeah, I think it's this. So this thing is a Mobius mapping, right? So it's a conformal mapping. We need to check that it actually sends the disk to a disk, and we're first going to check that it sends the boundary of the disk to a disk, and that will essentially do it for us, because if p is inside the disk, then p is sent to 0 by this thing, right? So if z belongs to the boundary of the disk, then let's write absolute value p of z. It's the same as the absolute value of this thing. Like this, and then let's multiply this by 1 over z bar, because 1 over z bar is just equal to 1, right? If we're on the boundary of the disk. Yeah? And then we can put this absolute value of z bar through. And we're going to have z bar, and then this thing will be z times z bar, but again, since it's on the boundary, this is just 1, so then this just becomes this, yeah, which is the same as just z minus p absolute value, and that doesn't change the norm, so then that thing's equal to 1. Yeah? Thumbs up if you're all happy with this. This is just a rapid rerun of stuff for you guys now. Okay, good. So this thing sends the disk into the disk like this. It's a Mobius mapping, so the image of any circle is either a line or a circle, therefore obviously a circle because it's contained inside a circle. And again, since this thing of this is equal to 0, it means it's got to map the interior of the circle to the interior circle. Yeah? So this is indeed a diffeomorphism from the circle to a circle, and we can slightly enlarge this class just by multiplying this by rotation, right? So e to the I theta Tp of z is another diffeomorphism of a circle. Yeah? Cool. All right. So that is all the background we need for Riemann mapping theorem. So what does Riemann mapping theorem say? I should feel like I should spell Riemann correctly, but I don't know how to. Suppose omega is open, simply connected set. And it's proper, which means it's not the entire set. That's not the entire complex plane. Then, for any Z0 belonging to omega, there exists a conformal mapping G from omega to the disk where G of Z0 equals 0 and G prime is bigger than 0, and this guy is unique. So it's based on the choice of Z0, obviously, but having chosen your Z0 with these conditions, G is unique. Okay, so I'm just about running out of time. So the power of this theorem is that if you have any arbitrary simply connected set, doesn't have to be bounded, doesn't have to be anything, right? It just has to be simply connected. This goes off over here. Then we can have a conformal mapping that turns it into just the disk, like this. And whatever point we've chosen, Z0, that can be mapped to 0. Okay? So conformal mappings, as you guys know, are extremely surprising in how restrictive they are, in that they preserve all angles. So if I put some sort of set of grid lines here, then these grid lines might be mapped to something like this, but they'll cross at the same angle throughout. Right? So if we are dealing with some problem on a simply connected set, we can conformally map it to the disk and then deal with that problem on the disk. This is this grand simplification we can do. So in PDEs and classical PDE questions, many PDEs are preserved. Their properties are nicely preserved under conformal mappings. So if you're trying to construct a solution of a PDE on an arbitrary simply connected set, you can conformally map it to the disk and then solve the PDE on the disk. And solving PDEs on the disk is massively easier, right? Solving the harmonic equation on the disk is a lot easier than trying to solve it for an arbitrary domain. You know? And that is part of the power of this theorem. You know? This was a big deal back in the day. Let me get back to you on that. I don't want to state something I'm not sure about, but let me talk about the extensions on Monday. But yeah, there are extensions of these theorems. The most famous extension is actually the uniformization theorem for Riemann surfaces, that says that any Riemann surface is conformally equivalent to three things: either the punctured complex plane or the disk. No, either punctured complex plane or the extended complex plane or the complex plane, something like this. Yeah, there are powerful extensions of this, but let me get to that. Let me get to that next time. All right, that's it for today. All right, good. See you guys. Have a good weekend.